Hello everyone, this is Tanisha. Welcome to my channel. I'll be teaching chemistry, physics, and math portions for the 12th grade. So let us start with chemistry chapter, the D and F block elements. So it is said that the D block of the periodic table contains the elements from this group 3 to group 12 in which the D orbitals will be progressively filled in the 4 long periods. So if we look at the periodic table, whenever you look vertical path, that will be your group. So this is group 1, group 2, and this will be group 3. So from group 3 to group 12 will be the D block elements. So this entire orange part, the middle part. So this group 1 and group 2 together are actually S block elements, and towards the right these are P block elements. So correctly in the center we are having D block elements. And when they say periods or series, it means horizontal path. So there is 4 series over here. 1, 2, 3, 4. And each series has 10 elements. So total number of D block elements will be 40. D block elements are also known as transition elements. Now they got their name from saying that whenever you're going to add electron to the atoms of these elements, it is going to fill the d orbitals. We all know, right? If we look at the electronic configuration, so this is the d orbital. There is 3d, 4d, 5d, 6d. So whenever electrons are added, you call it as differentiating electron, it will enter the d orbital. So that is happening with the elements in the d block. So that is what they meant by saying d orbitals are progressively filled. Similarly, there is something called as f block elements, where the electrons when added will enter 4f and 5f orbitals. Over here in the electronic configuration, again electrons will enter the 4f orbital and the 5f orbital. So these are placed as a separate panel at the bottom of the periodic table. These will be f block elements. From cerium to lutetium, these will be 4f, and then thorium to lawrencium, this will be 5f. So this 4f elements will be referred to as lanthanoids, then the 5f ones will be called as actinoids. Now lanthanum and actinium is placed here, but actually they are belonging to transition elements only. That means the D block elements, they don't belong to F block elements. They're part of D block elements. And we already know like these all elements are belonging to the same family, so they're just not placed over here in a vertical path. So they just are placed as a separate panel as we studied in 11th grade. So D block elements are known as transition elements, and F block elements will be known as inner transition elements. When it comes to this transition elements and D block elements, we are having 4 series: 3D series, 4D series, 5D and 6D. So 3D series will be from scandium to zinc, 4D will be from yttrium to cadmium, 5D will be lanthanum, but again from hafnium to mercury. This is 3D series. Next one will be 4D series, then 5D series. So as we already told, lanthanum is there, but we cannot just continue 58, 59 these atomic numbers because these are F block elements. So from 72 again we have to start. That will be hafnium to mercury. Similarly, the 6D series, actinum is over here, but you cannot just continue over here because this is F block element. So we will start from rutherfordium to copernicium. So keep in mind of the atomic number. It will not just be 57 to 80 or something like that. You have to say 57 separately, then write from 72 to 80 if you want to give the range of the atomic number for each series. And there are similarly 2 series in the inner transition elements, that will be F block elements. So that is 4f and 5f, as I have already told, cerium to lutetium and thorium to lawrencium. They will be called as lanthanoids and actinoids. So this transition metals, transition elements actually got their name from saying that their chemical properties were transitional between those of S and P block elements. So as I've already told, this is S block and this is P block. So when we observe these elements chemical properties, they were transitional from S block to P block. So that's why they got that definition. But then IUPAC gave a different definition saying that transition metals or elements will be those metals which have incomplete D subshell, either in neutral form or in their ionic form. So as you know, if we are talking about d block elements or transition elements, the electron will be filling the d orbital. So if it is incomplete, that means d orbital means what? Like we are filling the electrons like this when it comes to the electronic configuration. So in this is one orbital, in one orbital maximum 2 electrons can be there. So if there is s, p, d and f, remember odd numbers, that will be the orbitals. This will have one orbital, then this will have 3 orbitals, this will have 5 and this will have 7. So in one orbital maximum of 2 electrons is possible. So one orbital meaning electrons will be 2. So if 3 are there, it will be 6, because in one orbital if 2 are possible, in 3 there will be 3 2s are 6. Similarly over here 10. Similarly over here 14. So maximum in D there will be 10 electrons. You will fill the electrons like this. Don't directly fill one more electron over here. First one electron should be there in all the boxes and then only you can come back to pair them. So if less than, incomplete meaning less than 10 electrons are there, those all will be considered as transition metals. But one thing is that zinc, cadmium, mercury, though they are at the center of the periodic table, they are actually having 10 electrons. They are having complete electrons in them. So that's why even in the ground state, in the neutral state also, in their ionic state or common oxidation state meaning +2. So when I show the electronic configuration, you will understand that better. So in such a case, if there is full number of electrons in D, it is not going with the definition of transition metal. So you won't consider them as transition metals. They are a part of D block elements, but they will be simply not considered as transition elements, because transition elements meaning they should have incomplete set of electrons in the D subshell. Now the one thing that makes these transition elements different from the non-transition elements or the other elements is that again incompletely filled d orbitals and f orbitals. So they will have some new chemical properties and they will form some complex compounds, and it is very important to know about them, because when it comes to precious metals like silver, gold and platinum, and industrially important metals like iron, copper and titanium, all these are actually transition metals only. So we have to understand their chemical properties and compounds, then only we'll be able to use them. Further, the d block occupies the large middle section between s and p blocks. We have seen this, and the d orbitals of the penultimate energy level of atoms will receive the electrons. Penultimate is nothing but whatever valence shell is there, that is called ultimate. So the just before one is called as penultimate. Now 4s is the outermost shell. So this is called the ultimate. Just before that is penultimate. So D will be receiving electrons. That is what is D block. The D orbital will be receiving electrons. That is what they are saying. Penultimate meaning this D orbital will be receiving electrons. 4 rows, namely 3D, 4D, 5D and 6D. Now if we have to talk about the electronic configuration, there is a general formula given for electronic configuration, that is n-1d. In D maximum to 10 electrons can be there, so 1 to 10 electrons can be filled, and then ns. In S maximum of 2 electrons can be filled, so 1 to 2. So if you're suppose writing electronic configuration for 3D series, you will write 3D over here, and before S what number to write? Just one more than this. One more than that will be 4. If you're writing for 5D series, you will put 5D over here. Just add 1 and write before S. That will be 6. Now there is an only exception to this general formula is it is supposed to be palladium, because it is having Ns0. Instead of 1 to 2, it will have Ns0, palladium, if we see at the electronic configuration. See, for S it is having 0 instead of 1 to 2 electrons. So this is one exception for that. Now there are several exceptions also actually arising to this kind of configuration in middle. Like we are expecting a proper pattern when it comes to this elements to have a proper pattern in their electronic configuration, but there are some variations happening. The main reason for that is very little energy difference between these two orbitals. If they're having almost similar energy, electron can easily shift from this position to this position. So that's why in some scenarios, to achieve certain stability, it is not following a proper pattern, or it's not giving the expected electronic configuration. And one more thing we already learned in our previous grade, saying that half filled and completely filled or are relatively more stable. So to achieve that half and completely filled d orbital also, the electrons will shift and they won't give the proper pattern. So first, for 3D series we can see. So this is 3D series. You can remember this 3D series only. The other series not much important, but we can remember this 3D series. So scandium to zinc is our 3D series. These are the atomic numbers. So you write the electronic configuration using the Aufbau principle. So you can write 1s, then 2s, 2p, then 3s, 3p, 3d, 4s, 4p, 4d, 4f, and then start drawing the arrows like this. So follow the arrows. First is 1s, then 2s, then 2p and 3s, then 3p, not 3d, because still the arrow is passing through 4s. So 4s, then 3d, 4p, 5s. So then follow this rule. S can have maximum 2 electrons, P can have maximum 6, D can have maximum 10, and F can have maximum 14. So this is nothing but atomic number you will consider to keep filling it. So if you see over here, 4s is actually written after 3d. Actually 4s is coming before 3d, but because it is the outermost shell, like one with the maximum number behind that SPDF will be the outermost shell. Like here the maximum is 4, this is the outermost shell, that's why they have written it at the last, that is fine. But while filling the electrons, please fill this one first and then only go over here. So this is how you write the electronic configuration. And then if you see, there is like a proper pattern over here. And no need to write this completely every single time, because instead of this, one simple thing we can do is just put the noble gas just before that series. Like this is 3D series. So what noble gas is coming before this? Argon. So you can directly put argon in the bracket, because this is nothing but the electronic configuration of argon only. It will give up to 18 electrons. So that's why. And then because it's 3D series, write 3D. And according to our general formula, one more than that should be written before S. So 4S. So first 2, 1, then 2, 2, 2, 3. Now instead of 2, 4 over here, you have given that 1 electron over here and made it 1, 5. This is what is the half-filled d orbital, being more symmetrical, so it will be more stable. So d orbital is going to be like this. So if 5 electrons are there, you will fill them like this. So this is half filled. Half filled because the other pair is still not written, right? So this is half filled. If it is half filled, because of the symmetry, it will be more stable. And always these atoms and elements will prefer to be more stable. So that is why this is one exception. Then again it will continue with the same trend. 2, 5, 2, 6, 2, 7, 2, 8. Now again instead of 2, 9, that 1 is given over here. So it becomes 1, 10. So completely filled. If it is completely filled, it will be more stable. That is the thing. And zinc, if you see, for zinc if we see 2, 9, then this is 2, 10. So like that the trend is following over here. And we already know that zinc is not considered a transition element. Why? Because d orbital is completely filled. Entirely 10 electrons are there. Now you might get a doubt saying that okay, copper is also having 10 electrons, then why is it considered a transition element? You cannot say copper is not a transition element. It is considered, because now you just don't have to check the neutral state only. We have to check the common oxidation state or the ionic state, that is +2. These all are metals only, so they will give you positive charge, cation, because metals will always give the electrons. So this is the common state. So in this +2 level also, if they're having complete number of electrons, then only they will be considered as they will not be considered as transition elements. So if it is +2 state, this zinc will lose off these 2 electrons. +2 meaning giving off. So still 10 electrons are there, still it is completely filled, so it is not a transition element. But for copper, if you take +2 state, 1 electron will be gone from here. Always either add or take electrons from 4s first, because of per principle 4s is coming before 3d. You have written it only because it is the outermost shell over here. Now 1 is gone from here and 1 is gone from here. So how many are left? 9 is left. So it's no longer complete. So copper is still considered as a transition element. So this is for 3D series. Now if we consider the second series, that is 4D series, it's from yttrium to cadmium, 39 to 48 is the range. Now again, because it's the 4D series, you will write 4D, then 5s, because one more than that. And instead of writing the entire configuration, again you can see in the periodic table which noble gas is coming before 4D series. Before 4D series, you're getting krypton. This last group is nothing but noble gases. So you're getting krypton. So you can put that in bracket and proceed writing it in this way. Because it's 4D series, write 4D. Then one more than that, 5s. So always first start filling the S, 2 and 1, 2 and 2. Now from niobium to rhodium, actually again these are exceptional cases only, because you're no longer getting 2 over here. Instead you're getting 1 and 4, 1 and 5, 1 and 6, 1 and 7 and 1 and 8. And palladium, as I already told you, the only element which is not following the general configuration, having 0 electrons in its 5s orbital. So this is technetium. Actually, if they ask you, you have to know that this is the artificial and radioactive element. Now these last two will have just similar to these last two only. So here only thing is 3D and 4s. So here it will be 4D and 5s. 1 and 10, 2 and 10. Here also same thing. 1 and 10, 2 and 10. 1 and 10, 2 and 10. All the reasons are same. Over here, because for the stability, it will have given 1 electron over here, so it becomes 110. And this copper, silver, gold and roentgenium, though they have 10 electrons, when it comes to their d orbitals, it is completely filled, still they are considered as transition elements, because +2 state if you take, that is the ionic form, they are having incomplete ones. And if you look at the last elements of everything, zinc, cadmium, mercury and then copernicium, they are all having 10 electrons. They are completely filled, even in the ground state, even at the +2 state. So they will be not considered as transition elements. Then next series will be 5D series. So in 5D series, you will write 5D first, then 6s, then lanthanum, it is 57 as already discussed, then from hafnium to mercury, from 72 to 80. So then 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 2, 7, and here it will change off. Instead of 2, 8, it will become 1, 9. And this will be same as these two only, 1, 10 and 2, 10. Next will be 60 series, 60 and 7s. For this, if you have to write the noble gas, you will write, this is 3D, 4D. So 5D series, you will write xenon. And for 60 series, you can write radon in the brackets before writing 5D, 6s and 6s, 7D, 60 and 7s. Before writing that, you can put the noble gas in the bracket. So here also it's following the same thing, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. Still, but these last two will remain same as these two only. So this is the same thing they're saying, that zinc, cadmium, mercury and copernicium, they're having completely filled in the ground state, as well as the common oxidation state, that is +2. So don't consider them as transition elements. Then the d orbitals of the transition elements protrude to the periphery of an atom. Basically they're saying that d orbitals are towards the border of the atom. So if then at the border, what will happen? They'll easily influence or interact with the surroundings molecules, and they can also get influenced by the surrounding molecules, because they're at the border, they can have more contact with the surroundings. And in some respects, ions will have DN configuration. Ions meaning they are metals, so they will lose electrons. Positive cation will come, so they will be losing electrons. They will be losing 2 electrons, then 3 electrons. Then what will happen in the electronic configuration? So if they lose of 2 electrons, the entire 4s is gone. So only d electrons will be left. So that is why they are saying Dn. Dn. Generally, these transition elements will never show +1. So mostly they are showing +2. So entire 2 electrons will be gone, meaning S is gone. So only D will be there and some electrons will be there in that. Now if suppose you're getting some two ions that are having like D6 and D6, if that is same, then they will have similar magnetic and electronic properties. And with partly filled d orbitals, there are some characteristic properties, variety of oxidation states. Like one element will only have many oxidation states, which we will see in further, and formation of colored ions. They will form colored ions, and there will be complex formation and variety of ligands. Like ligands are basically, you can tell, any species, any ion or atom or compound which is going to give a pair of electrons and make a bond with a metal. So actually these are responsible for the colored ions also, which we will learn later. Then transition metals can also exhibit catalytic property, meaning they can act as catalyst, those which are used in a reaction to make the reaction faster. So to accelerate, they won't participate in the reaction, they just reduce the time of it. And paramagnetic, when there is like unpaired electrons, you can see in the electronic configuration, then what will happen, they will get attracted to the magnetic field. So these properties also you can see in the transition elements. Generally, if they're horizontal row, they will have similarities, but down vertically also, if you see group, there are certain similarities, the trends, so which we will be seeing. Now you can say, there is a question that saying that you can say scandium is a transition element but zinc is not. Why? Same thing, scandium, if you see its electronic configuration, d orbital is not completely filled, so you can call it a transition element. But for zinc, it is completely filled, even in the neutral state, even in the +2 state. That's why you can call scandium as transition element but not zinc. Then they are posed another question saying that, okay, silver is having 10 electrons, it's completely filled, then why is it a transition element? Same reason that we have given, that if you take +2 state, here ns1 will be there, 5s1 will be there, so 1 electron will go from there, 1 electron will go from here, 9 electrons only will be there. So not only neutral state, check the +2 state also. So in such a case, it's having incomplete number of electrons, so that's why you can still consider it as a transition element. Now there are certain physical properties. So most of the transition elements, they are showing metallic properties. High tensile strength will be there, ductility, they can be drawn into long wires, malleability, you can beat them into thin sheets, high thermal and electric conductivity will be there, lustrous, they will be shiny, sonorous, if you're going to hit them, you will get a ringing sound. All these are there. And also there will be, most of the cases in room temperature, there will be solid except for mercury being in form of liquid at room temperature, and most of them are hard also. And there is there are certain exceptions saying that zinc, cadmium, mercury, these are not hard, they are soft. They might ask you the reason why are they soft metals. It is because of low enthalpy of atomization. Enthalpy of atomization meaning, generally if we see any of this element, any of the metal, they will be bonded like this, they're solid, right? So one atom will be bonded like this, tightly packed it will be. So you can tell it as a type of covalent bond, and we will refer to it as interatomic metallic bond mostly. So there will be electrons in here which will be actually delocalizing, like they'll be moving from here to there, there to here. The free electrons, the unpaired electrons, mostly unpaired electrons, meaning if I just draw one thing in one box, this will be unpaired because it's not having another electron, right? So that electrons, they will be free to move. So if they are free to move, this nucleus will also attract this nucleus also will attract it, this nucleus also will attract it. So it will be a strong bond, it will be more stable. Now atomization, enthalpy of atomization, meaning how much energy should I provide so that this atom breaks away. This atom should come out of that bond. Now if bond is really strong, I have to provide more energy, so then enthalpy will increase. But for zinc and all, what is happening, if you look at the electronic configuration, if we look at zinc electronic configuration, there are no unpaired electrons only. In s1 orbital, meaning one box is there, 2 electrons are there. Singly, one electron is not there. In D also 5 boxes are there. One box, 2 electrons are there, total 10. So there is no unpaired electron only. Like if there is no unpaired electrons, delocalization will happen little less. Same with other also, zinc, cadmium, they're all having same electronic configuration only. So if delocalization is happening less, then the bond will be weaker. So I would have to provide less enthalpy only, less energy I can provide, then it will be low enthalpy. So that is why they are soft. This is the reason for this exception. And generally one more thing is that their melting points and boiling points are also very high. Why is that? Again, there is a strong interatomic metallic bond. It's a type of covalent bond, this bond. There is unpaired electrons, free electrons which are delocalizing. Atoms are tightly bounded like this. Because it is very strong bond, you have to provide a lot of temperature in order to convert them into liquid and then gas, and then also to break away the atom. So generally transition metals will have high melting point, high boiling point, and high enthalpy of atomization as well. And generally, if you can see in this graph, first along the series, if you see, this is 3D series, 4D series, 5D series, horizontal, if you keep seeing, it will increase. First the boiling points, melting points will increase, but then again it is dropping. Now there is a reason for this also. If you see over here, in first scenario, the melting points will be gradually increasing only. Why? Because there will be more number of unpaired electrons. But as if you go along the series increasing, the unpaired electrons will become less. Here only you see. If we see over here, one unpaired electron is there, then two unpaired electrons are there, because consider d orbital. So over here 2 are there, then 3, all these are unpaired only, then 5, all these are unpaired. But when it comes to 6, as you're moving along that series, one more electron should come over here, it got paired. Unpaired electrons are reducing, then again 7, then again 8. If unpaired electrons are going to reduce, then delocalization of that will happen less, then bond will become weaker, so melting point and boiling point will also drop. This is one more reason for that. Generally, whatever element is having this d phi in their electronic configuration, they have to go to the maximum state, like chromium, molybdenum, tungsten. If you see here, chromium is having 5, molybdenum. Tungsten, you might think there is no 5, but actually if you are going to give one electron from over here, then it will become 1 5. That is also accepted, because if 2 4 or 1 5, they're having almost same energy. Though in exam write this because this is given in the textbook, but generally if you're giving one electron over here and making it 1 5 also, it will have similar sort of energy, so it is fine. So these generally, if they're having this phi in them, their melting point, boiling point is increasing. That's why they're at the peak. But again, there is anomalous property. There is a exception for this, saying that manganese and technetium, they're falling. Look, their melting point and boiling point decreased. Why is this happening? Because if we look at their configuration, yeah, so generally for manganese, phi, if it is there, we already know that it is half filled, that it will be more stable. If it is more stable, what will happen when there is like this bond? So what will happen is there will be more forces of attraction between this electron and this nucleus. See, this electron should be able to move over here, here, here freely. Then only many nucleus will be able to attract it. It will become a stronger bond. But what is happening? If it is very stable, this electron doesn't want to go only, because it will be gripped tightly to this nucleus only. So this cannot move over here and here as expected. So what will happen? Delocalization will become less. If delocalization is becoming less, the bond will go weaker. So that is why their melting points and boiling points will decrease. Whenever the bond is weaker, melting point, boiling point, enthalpy of atomization will decrease, because it will be easier to break the bond. If it is easier, these things will reduce. Now you might say, okay, then for chromium, for This tungsten, molybdenum also they're having 5. There should be stability. Why is that their melting point and boiling point going higher? It's because of the unpaired electrons. 1 that is being unpaired. This is 1 5. So 1. So again they're unpaired. So one extra unpaired electron is there. Meaning if more unpaired electrons are there, more delocalization can happen. They will move more. More electrons are there to move more. So their bond will become more stronger and melting point will increase. But here 2 is there. In one, S meaning one box only is possible. One orbital. 2 electrons are only possible. And 2 electrons are kept in that, unpaired electrons have reduced. That's why for manganese and technetium. Again you might think 5 is not there here. You can just send it over here and make it 2 5 also, because they're almost having same energy, 1 6 or 2 5. So that is the anomalous property for this. Then high enthalpy of atomization also will be there. Now they're telling, if you look at this graph, there is this maxima at middle of the series. It is reaching the maximum point, and that is indicating that there is unpaired electron per d orbital, favorable for strong interatomic interaction. So that means they're saying the same thing. If there is unpaired, if you look at over here, this is 3D series. So scandium, titanium, vanadium. So if you look at the electronic configuration, there will be unpaired electrons. 3 unpaired electrons are there over here. So they will delocalize more, bond will get more stronger. So you will need more energy to break the bond. That's why high enthalpy will reach. Similarly for here also, more unpaired electrons will be there. So it will reach the maximum curve. So we have covered few topics in this video, and several other topics will be covered in the next videos. So if you liked my content, please like this video, and if you want to further study more chapters and more topics in this channel, and you have to get a notification for that, so please subscribe. And any kind of feedback to be given and any doubts, please feel free to leave comment in the comment section. Thank you. See you in the next video. Bye bye.